So thank you for being here. First of all, this is the talk on structural prediction for CRiSP inverse kinematics learning with misspecified robot models. And this is a joint work with Raffaello Camorianoћ, Lorenzo Rosasco, and Carlo Ciliberto. And in this work, we will introduce a novel data-driven approach to computing the inverse kinematics of robotic models from examples leveraging some recent results on structural prediction in machine learning. But first, let's start by very quickly introducing the classical problem of inverse kinematics, where the idea here is that we have access to some robot which can be seen in configuration space, which is the space of possible configuration at the joints, for example, and task space, which is the position, the orientation that such robot can obtain for some kind of task. And usually, the problem of inverse kinematics consists in given a function g, which is the forward kinematics that maps the configuration to then the vector position and orientation, finding a function f of x that is in some sense the inverse of this function. So more specifically, when composed with g, it's the identity. And while usually computing the forward kinematics is quite easy, computing the inverse one can pose some challenges, and that's why we try to propose a data-driven method for this. But first of all, one might ask, why data-driven? Well, the analytical approaches are much studied. There is a lot of literature on those, but there are usually some core issues that one might want to overcome, like they need to be derived from scratch for every model. They might be complicated and feasible for some robot structures, or they can also be very sensitive to errors in the mechanical model. So to overcome this issue, we propose a machine learning-based method that looks at some examples, trying to estimate the inverse kinematics. But first of all, so let's check some of the challenges that trying to tackle this issue with a data-driven approach poses. The first one is that actually we're dealing with a structure problem, which means that we're trying to learn a function f that maps from the task space to the configuration space, and the configuration space, so the output space of our function, is linear, but also poses some hard constraints that are given by the joint limits of the mechanical robot. So considering traditional methods such as regression will not give us very good results here, because those methods are usually not aware of the structure of the output space. A second problem stems from the structure of the losses usually used for this kind of task. So losses that look at the difference in the joint space. So consider this very basic example where we have two training points, x1, x2, that are our data set with, say, the outputs, the targets given by the angle that reach those points, x1, x2. And so we want to learn now a linear classifier, w, that we will use to predict the position. So joints that attain the x test, which is the same as x1 and x2 in this case. So actually this should be a very easy problem where we should easily overfit the two training points and predict with perfect accuracy our goal. However, if we do this, actually we end up with this. And the problem is that if we go and look into the math, we see that usually these classifiers are computed as a linear combination of the joints, of the points in the joint space. And therefore, if we look actually at the proposed solution here, we'll see that this, for example, theta hat 2 is exactly the mean between the theta of the first example and the other theta of the second example. So it will be exactly in the middle. And so it ends up that when we try to predict these points, we have the predicting point that will be very, very much different than the target one. So another remark which is important when considering this kind of task is that usually the actual goal in this kind of setting scenarios is not actually defining explicitly a function f of x, which is the inverse kinematics, but a function such that when composed with g is approximately the identity. An example here of can be seen, for example, in trajectory reconstruction, where given a point or a sequence of points, we want to reconstruct, so we want to know which set of joints attains back the goal point in the task space. So let's see what is the proposed method that we introduce to tackle this kind of tasks. And well, this is the predictor we propose to use. So f of x has this kind of form, which it might look a little bit intimidating at first, but actually it's quite simple. Essentially, it's composed of two parts. There is a functional, which is like a weight summation of losses that depend on the targets, so on the joint configurations. And you can see here that these weights, scalar weights, depend only on the inputs, so only on the position in the space. And once we have this functional, we want to find the y that minimizes this function. So it's like some sort of weight barycenter of losses. And actually computing this specific predictor consists of two steps. The first step is training, where we evaluate the alphas, which can be outlined once you have access to the training points. And this process is akin to solving a kernel range regression, where the most cumbersome operation is the inversion of this matrix, which is defined based on some kernel function. The second part is instead minimizing, finding the minimizing y of this functional, and actually this depends on the considered structure loss that we use in the structure estimator. And specifically, one of the contributions we make in this work is that we propose to use a loss which is very different than the loss used in traditional in this kind of task, and is the following loss, where we suppose we have access to some kind of approximated forward kinematics of our robot, and then we measure the error by mapping again the proposed y back into the task space and looking at the actual distance from the target in the training set, and the actual distance in terms of orientation, again with respect to those present in the training set. And once we have this, essentially we are looking at, if you want, at a metric that measures the true loss on the true final task we're interested in. And we propose to minimize this following functional by using LBFGS for constraint minimization, a very well-known study algorithm in the literature. So given this estimator for estimating the inverse kinematics, we test it on the task of trajectory reconstruction specifically. So suppose we're given a sequence of points in the task space, and the goal is one by one to find the joint configurations that reconstruct those points sequentially. And we do this with our CRiSP structure estimator. And first of all, what we do here essentially is that we compare our method with other data-driven approaches. And you can see here qualitatively the results. So we see that CRiSP is very good at reconstructive trajectory, while the three other data-driven approaches perform very poorly, and we argue that this is caused by the fact that all three of these actually use a loss into the joint space, so they're not very good at measuring the distance between different sets of configurations that actually reconstruct correctly the solved trajectory. And also more specifically, while these two actually are structured methods, so they're aware of the constraints on of the robot, the neural network is not even a structured approach, so it may happen from time to time that actually the predicted configuration is not a valid configuration. And so what we ended up doing is just clipping those values inside the joint limits of the actual robot. Actually, we have a bunch of more quantitative experiments in the paper if you're interested in that. Then what we proceed to do is also to test how robust is our method with respect to the supplied approximation of the forward kinematics G. So as we have mentioned, we don't have to use the perfectly well-known G, but we might use some kind of G that has some errors. So what we do is that we build a G tilde injecting some kind of noise in the model. So actually we end up using a forward kinematics of a different robot that has links with different length. And we compare the results of the prediction again of two trajectories, an 8 and a circle, which selected the least square method, which is an analytic method that usually when it has access to a perfect G, so to a perfect forward kinematics, can very precisely solve this kind of problem, attaining very small errors. But we can see here that as the error, so the bias in G tilde increases, obviously both of the methods have their average error increasing, but our proposed method, CRiSP is much more robust and much more precise than the analytic one. And actually, this trend can also be observed when we try a different kind of error, a different kind of bias in the G tilde, and in this case is in the angles at the joints. Again, CRiSP-FK, since it's a data-driven method, so can look at a lot of different examples, is much more robust to the bias introduced in the G tilde when compared to the analytic method. Now, to give say a glimpse of what happens when we test this algorithm on a more realistic scenario, we also apply it to the PANDA simulated robot. So this time a 3D robot, much more complicated, and we try to see what happens when we test it on two trajectories, so a circle and a spiral. And here we have a small video giving you an idea of what happens first when actually we try to use a traditional data-driven method that doesn't use a loss in the task space. And here we'll try to reconstruct a simple circular trajectory with a structure estimator that actually uses the loss in task space. And you can see that in red, this is the error. So the predicted values are very, very stable, specifically also close to the kinematic singularities of the robot. And you can see that actually the predicted or constructed trajectory is quite poor. On the other hand, when we use CRiSP-FK, you can see here that it's definitely much more stable. The error is qualitatively very, very small, and usually there are no problems. You can see just as much of red as the error. Similarly, we tested also CRiSP-FK again on the spiral, and we can see that the error is still very, very small. We also compare this method on the PANDA simulated robot again against an analytic method, again SDLS, and you can see again qualitatively in yellow, CRiSP-FK is much more precise than SDLS. And if you're interested, obviously we have also a bunch of experiments in the paper where you can see that almost every time CRiSP-FK outperforms in its analytic counterpart, SDLS, specifically when the bias in the forward kinematics model starts to increase. So to conclude, the main contributions of our work are that we introduced data-driven methods for learning the inverse kinematics of robot using some recent results from structural prediction machine learning. This method that we introduced is robust to model misspecifications. And we did not talk about it, but there are some nice statistical guarantees about our method. And we also released the code, which you can find at this link. Some future work includes trying to bring uncertainty in the prediction we make, so trying to understand how much we can trust in prediction, looking for an active selection of the data set, because we actually noticed that our method looks to be very local with respect to the points that it uses to make the prediction, and also trying to directly estimate the G tilde instead of using one supplied by the user, using one estimated from the data points, and so having an end-to-end learning pipeline that estimates first the forward kinematics and then the inverse one. Thank you very much for your attention, and I'll be more than happy to answer your question now.
Thank you very much. We have time for one question. Anybody has any questions, please raise your hand or type it in Q&A. I have one quick question. How does your method handle the kinematic redundancy when there are possible several inverse kinematic solutions for one forward kinematics?
Okay, so this is a very good question. Actually, it's one of the first reasons that brought us to look for such a method. And actually what happens is that if you look at the estimator, you can see that it's consistently minimizing this functional, and this function usually is non-convex. So it has different solutions, and each one of those different solutions corresponds to one of the possible solutions that come up from the kinematic multiplicities. So what we do is that, for example, in the case of trajectory construction, we can just initialize the prediction of one of these points from the solution of the previous point. So this ensures that the new solution we get for the next point will be close to the previous one. And so we have that the path in the joint space is going to be smooth. If you want instead to look for other ones, then you will have to play a bit with the initialization of this minimization process.
Interesting. Thank you very much. If there are no questions, we can go to the next presentation.
Thank you.